In this tutorial we will simulate a wheeled inverted pendulum using ROS2. I will explain basic ROS2 package structure and how to create a gazebo simulation model. As a model we will use Segway. Probably Segway is the most widely known industrial implementation of inverted pendulum. Despite futuristic look, control method of Segway is simple, and it can be easily simulated using ROS. Firstly, we will install the required packages. Install the Python 3 common extensions. Colcan is a command line tool to improve the workflow of building, testing, and using multiple software packages. It automates the process, handles the ordering, and sets up the environment to use the packages. Next, install the Foxy Gazebo ROS packages. This package provides interface for using ROS with the Gazebo simulator. Next, install the Foxy Zacro package. Zacro is an XML macro language. With Zacro, we can construct shorter XML files by using macros that expand to larger XML expressions. Now I am going to explain the purpose and structure of each package. Please download the Segway Foxy zip file and open the source folder. In the robot description folder we have Zacro files and URDF files describing how robot links and joints are connected. In the Segway control folder we have Python scripts which subscribe to joypad, IMU and output velocity of the robot so that it can keep standing upright while moving forward. In the Segway Gazebo folder we have files describing the world model and files to visualize the robot. Here we also have files necessary to launch the simulation. Let's see each folder in detail. In the URDF folder we have Zacro files of the body, wheel and IMU. The Zacro file format is absolutely the same as that of ROS1. In the robot folder we have Zacro and URDF files of the robot. The URDF file is generated using Zacro command. Note that to run the Zacro command successfully, firstly we have to build this project, secondly run the source command, thirdly we have to move to this directory and then execute the Zacro command. Now let's see Segway control Python script. Initialization is done by calling the init function. This must be done before creating any ROS nodes. Here, instances of each class are created. In the Segway controller class PID control is done. Here vel message of the twist message type is defined. Twist message expresses velocity in free space broken into its linear and angular parts. It is used to publish target velocity values for diff drive controller. In this part PID gains are set. There are several ways to calculate PID gains theoretically, but since we have a gazebo simulator, the fastest way to find proper PID gains is to adjust it in the simulator. Here, a publisher is defined. The topic name is defined in the SDF file which we will see later. In this line, the timer is defined. This line means that function timer callback will be executed every 5 milliseconds. Here, the difference between pitch target value obtained from the joypad and actual pitch angle obtained from IMU is calculated. In this part, integral error is calculated. Note that the area of trapezoid is used. Here, Segway linear velocity is calculated. Since this is a single input and single output system, a simple PID control is enough for this problem. Finally, calculated linear velocity and angular velocity value are published. In the IMU subscriber, obtained quaternions are converted to pitch angle. This pitch angle is used to control the robot as we saw previously. In the Joy subscriber, axes data is converted to Segway target pitch angle value and target angular velocity values. Note that depending on the coordinate system of your robot and the joypad used, you may need to reverse joypad axes values. To publish and receive topics simultaneously, a multi-threaded executor is used. After instantiating a multi-threaded executor, each node is added to the thread pool. The thread pool maintains multiple threads waiting for tasks to be allocated for concurrent execution by the supervising program. Then threads are created and started for multi-threaded executor. In this part, the program checks with frequency of 2 Hz whether a node is active or not. Now let's see the launch file. In ROS2, the launch file must contain generate launch description since Culkin will expect to find this function while building the process. Also generate launch description function must return a launch description object. The main function is not needed in this script. Now let's see the Segway Gazebo folder. The Models folder contains a model of the Segway. To make the Segway visible in the Gazebo and to implement various plugins, an SDF file is required. To make the SDF file, we need to get back to robot description robot directory and convert URDF file to SDF file. Here is how to do it. As we did when we converted the Zacro file to the URDF file, we need to execute the source command and move to this directory. Then execute this command. GZ command converts URDF file to SDF file. Now let's go back to the Segway folder and see what is inside. In this line the directory of the STL file is specified. Note that we have to change directory of each link from that of URDF so that Gazebo can find mesh files for collision calculations and for visualization. Here, the IMU sensor is defined. The setting items are the same as for ROS1. Basically, this setting should be applicable to any simulation. Here diff drive controller is defined. The initial required topic name is command vel, but since we define namespace as Segway, the topic that should be published is Segway command vel. Also note that in ROS1 wheel radius is used but in ROS2 wheel diameter is used instead. Now let's look into the model file of the Gazebo world. The file structure itself is absolutely the same as the world file of ROS1, but in ROS2 we also should include model of the robot we are going to simulate. Here, initial camera angle is defined. It is convenient because we don't have to adjust simulation field every time we start the simulation. Now let's see inside launch files. Here we specify the URDF file directory and open the file. In this part we launch the robot state publisher node. Note that we must set the robot description parameter or the node will fail to start. In the Segway simulation launch PI we launch all files to start the simulation. Here, Directory of each package and world file path is specified. Here we launch Gazebo. This part is always the same in every simulation, so just take it as it is. In these lines, launch files we defined in other packages are included. Here we launch Joy node to publish joypad inputs as Joy topic. Also, we should modify the CMake file. In this package we have added this part to the automatically generated CMake lists text file. Install tag specifies rules to run at installation time. The directory form installs contents of one or more directories to a given destination. The destination specifies the directory on the disk to which the file will be installed. The second install command installs the library. Archives and library files will be exported to the lib folder. In the export tag, Gazebo model path should be added. Otherwise, ROS will not be able to find the path to the Gazebo models. Note that similar modifications should be done to the CMake file and to the package XML file in every package. Now let's do the simulation. Please download zip file from the Google Drive and extract it to your home directory. Move these models to the Gazebo directory. Move to the Segway Foxy directory and execute the -build command. Connect your joypad to the computer. To launch the simulation, execute the source command and launch the Segway sim launch py script. As Gazebo world shows up, you should be able to move the Segway around with your joypad.